and how to make like some standard function blocks like comparator, decoder, mux to implement regular Boolean function. Have you learned those things in a sophomore class called logic design? Do you have any idea? How is mux implemented? Mux is not implemented with ands and ors. In VLSI, it's implemented with only pass transistors. That's why we call mux a very fast and very small circuit. If you think of muxes as being made up of ands and ors, no, that's just conceptually, just for your easy understanding. In fact, it's made up with only pass transistors. This is an N-gate, an N-type transistor, pass transistor. We just want it to be on or off. This is a P-type transistor used as a pass transistor. We just want to make this as an on or off circuit. And we connect these two ends together and call this the output. This is X, this is Y, and these two signals is the select signal. The select signal says when I'm high, then X goes through to the output. When I'm low, then Y goes through to the output. Okay? So this can select among between the two. This is a mux circuit. Can you see how simple it is? Whereas if you want to make it up with ands and ors, then you'll say, I need to have an AND gate, another AND gate, X, Y, and this is the select. And OR these two outputs together to form the final output. Can you see how complex this circuit is? In real VLSI design, this is a true implementation. Can you see how small the circuit is, how fast it can be? That's a mux. Okay, anyway, that's so-called the logic level. And if you want to really understand the logic level, you need to have some knowledge about the circuit or physical layer abstraction so that you know it can be implemented in this way. Okay? So we call this circuit, or sometimes physical layer. Above that, what is it? The organizational level. The organizational level says how many ALUs we want, how many pipe stages we want, and how to connect them together. So that's called the organizational level. Just like for your apartment, for our building on this level, we want to know we need to have a classroom here. This is the door. Door opens in this way. And this is yet another classroom. And since this classroom is bigger, we need to have two doors opening to the inside. And here, other classrooms. So maybe we need to have a restroom here in this corner and another restroom here in this corner. This is called the organization, right? Above the organization level, what do we have? Architectural level. Architectural, in terms of building houses, the architecture defines how the house looks like, what it is used for teaching purposes, for hotel, for public facilities. All different uses will have different requirements, different features of the building. Yet we don't care too much about whether we use bricks or cement to build a wall. Okay, we don't care too much about that. That's for the lower levels to determine. Above that, what levels do we have? Maybe we have higher levels, like compilers, OS applications, and whatever possible uses of IT, information technology, we can have. Okay, so here we are. We're on the architectural level. For the organization level, it's somewhat has a lot to do with the reality, how it can be built, actually built. But for the architectural level, it has something to do with art. How do we want it to look like? What kind of mood do I want my product to show? Okay? Does that give you a good picture of what why we're taking this course? So far, so good? Okay, so in order to be a good architect, if you want to make a good architect, what do you need to know? You need to know all the advancements, all the fundamental knowledges of the lower levels. Also, you need to know all the knowledges of the upper level. This is the same for every level. So I want you to know something about computer organization, computer logic design, and semiconductor technologies. At least some fundamental ideas so that when I say, maybe we should build the computer in this way, then you can make your own judgment whether what I'm saying is feasible or not. Maybe we should design the computer in that way to suit the needs of a certain new language like Java. Then you need to know something about Java. Maybe I want to build this chip for a cell phone, then you should know something about communications and all kinds of tricks we have on a cell phone. Okay? Let's go back to the foils. The foils are always easier to understand because you have something on the paper for you to read. Okay, computer architecture versus instruction set architecture. Long time back, like 4 decades, 5 decades ago, when we talk about computer architecture, what we taught in this course was computer arithmetic. In other words, we cared more about how to design multipliers, adders, and things like those, like functional blocks, those functional blocks which are more fascinating than the register files. Register files are very structured, very regular, not many tricks you can play in it. Okay, but for multiplier, there can be tricks. You can build faster multiplier like what I told you last week using the Wallace tree, using a Booth algorithm. For the adder, you can look ahead the carry to shorten the carry propagation chain. Okay, so if I ask you, in order to add two 64-bit numbers, 64-bit and 64-bit, in order to add these two numbers, first, the circuit you're going to use is combinational or sequential. Remember combinational and sequential? Combinational says whatever is given as the input, you always get the same output. Sequential says, no, not just that. Other than the inputs, you still have memory inside. So the output depends not only on the inputs, but also on the state of your circuit. Okay? So when we add, do we use combinational circuit or sequential circuit? Tell me which kind. Combinational? Don't you remember we have a carry chain? That chain always depends on the previous position addition. So is that combinational or sequential? Sequential? So 5 adds 10 may get different results? I thought I'm the one who's supposed to laugh. So is that sequential or combinational? The answer is, of course, combinational. With any combinational circuit, we always can add using, we always can produce the output using a level of AND gate and a level of OR gate. In fact, a single OR gate, right? And OR, and everything is done for combinational functions, right? So can we do that for add? Yes or no? Can we OR, AND OR, and get the final sum? If you think the answer is yes, then please raise your hands. If you think the answer is no, then please raise your hands. If you haven't raised your hand, then please raise your hand. What's wrong with you? Being a graduate student, you need to make decisions all the time. Sometimes things don't have standard answer. So you always to choose among all the alternatives. Wiser people have wiser decisions. So an adder is combinational. If you think so, raise your hands. I do think it's combinational. The answer is only we don't have such a big AND gate. My big AND gate says, if these two bits are, we generate a carry, and if these two bits, then we generate a carry, and if these two bits, then we generate a carry, and so on. And if these two bits are 1, 0, or 0, 1, or 1, 1, then I'll produce a 1 here. See? Very clear condition. Just the equation is not complicated, but too long. Okay? Simply because it's too long, so that we want to use simpler modularized circuit called full adder to do bitwise operation and ask the higher order full adders. I'm sorry, I said full adder, but I wrote half adder. And ask the higher order full adder to wait until all the lower order full adders are done. Okay, we use time to trade circuit complexity. But really, we can have only one AND and one OR and get it done. Get the carry out done. Similarly, one big AND and also the final OR used by everybody to get this highest order bit done. Okay? How many ORs do we need? In such a circuit, how many ORs do we need? Can somebody tell me? The answer is every output will require one OR gate. So in other words, we have 65 outputs from 2 to the zeros to the 64th, the carry out bit. So we need to have 65 OR bits to realize the whole big adder circuit. So finally, we know the adder, no, not exclusive OR. The adder is a combinational circuit, which is very trivial. Okay, and we can use all the smart ways to design our adder to make it faster or smaller in size. A whole range of products that you can choose from. Okay, that's what we taught in computer architecture back in the 60s, 70s. Later, computer architecture course switched to teach you how to design CPU. Tell me if CPU is equivalent to a computer system. Is it? It's just like, is engine equivalent to an automobile? Of course not. So next, define what a CPU is for me. Is it your turn? Tell me if CPU is the smartest guy in the system. Is it? Tell me if CPU is the most powerful guy in the system. Is it? Okay, so you think it's the smartest, but you don't know if it's the most powerful. So if the CPU is the most powerful, do you know?
I think it is.
Okay, let me tell you how. I really do have a lot of pity for the CPU. Let me tell you what the role of the CPU is. Does CPU know what the upcoming instruction will be? What the next instruction it's going to execute will be? Does it know? No, it doesn't. That's why after every fetch, you will have to decode. I don't know what I'm going to do next step. Question number 2. Does it remember what it has done just then? The previous instruction, does it know what it is? No. So CPU is a very poor guy. Whatever I want it to do, it does it. Don't argue, no bargain. Do it. What do I want you to do? I haven't decided yet. You just wait. Okay? So CPU is really not powerful at all. Who has the power to determine what's going to happen? Perhaps OS, perhaps the application program, but never the CPU. The CPU is very powerful in terms of executing a single instruction. It is the only thing that can do this task. And for every task, we need only one guy to be able to do it, right? Memory can do something the CPU cannot do. I/O can do something the CPU and the memory cannot do. Everything has its own unique function. Okay, so now can you see how poor the CPU is? Okay, that's the CPU. We spent about 2 decades teaching you how to design good CPU. And then later, we have switched to a more systematic approach. We started to teach you more like cache memory, like interconnection network. Where's the interconnection network used? When I talk about interconnection network, it can be ad hoc, like within the CPU. I just link whatever needs to be linked together using my interconnection network. Any particular regular form? No regularity at all. But sometimes I want to link a number of systems together. These systems may be homogeneous. By the word homogeneity, I mean all the systems are equally powerful, equally important. Okay, if they're homogeneous, then the way I link them together, maybe I may use a bus. I may use full connection. I may use star, I may use ring, I may use multi-stage, whatever, all kinds of regular interconnection networks. Okay? And then we started to teach you something like vector processing, media processing in computer architecture. And later on, we started to tell you how to distinguish among microcontroller or embedded processor, general purpose CPU, special purpose CPU, maybe for workstation, maybe for server, okay? Other than on top of the CPUs, maybe embedded system, personal computer, workstation, graphics computer, and the server. Sometimes even like data center. Thousands of computers networked together. Okay, something we haven't taught you is like the internet, the security. But we do touch a little bit on the database and talk a lot more about like compiler. Who uses your CPU? Who is the user of the CPU? The user always counts, customer always comes first, right? So who's the customer of our CPU? What? The OS? Not really. If we call the OS if we call the OS the CEO, then who directs the engineers? Not the CEO. Could be the manager. Okay? And the program is the customer of the OS, even at an even higher level. So, what's your answer?
The input and output devices.
Oh, no, those devices are mostly passive. Instruction is too low level. Right. Compiler determines what machine code will look like. Right? And the machine code drives the CPU to go ahead or to branch to somewhere else or to terminate the machine program itself. Okay, so these are the things you need to know. Let me tell you one more thing before we go back to the foils. How many of you have seen assembly programs? Everybody? Okay. So the assembly program may have a statement called ORG to begin with. And then you have adds, subtracts, loads, stores, and maybe branches, and maybe jumps, and maybe calls, and maybe I's, and maybe O's. All these mixed together, and eventually you have another final instruction. What is that? It could be called break, stop, halt, exit, whatever. Okay, they're all equivalent. So if the final instruction is an exit, it says exit. Is that a real instruction or is that a pseudo instruction? Just a signal telling the system no more, no more. So exit, what is exit? Or halt or stop? Are there operations involved? Good answer. That's a system call. It doesn't have to clear the register. It doesn't have to clear anything. Just indicate those things are no more used for trash. Okay? Or you don't even need to know that. Every program will need to initialize any register that it's going to use later. So if you don't, then you get a random value out of it. So the exit is really a system call, doing whatever is necessary and returning the control back to the OS or the monitor for simpler systems. So that's a very meaningful and with a lot of operation in it instruction. That's a useful instruction. Okay, you need to understand all these, not for this course, but for every CS course. Are we ready for computer architecture versus instruction set architecture? Okay, instruction set architecture. Tell me why it's important. Before that, I need to tell you what the instruction set means. The instruction set means machine instruction, not even assembly instruction. Assembly instruction to machine instruction is not one-to-one. For instance, your multiply assembly instruction may map to a subroutine, system subroutine of the machine instruction because your hardware cannot do multiply. Your hardware can only do add and shift repetitively. Okay, so assembly to machine is not one-to-one, although mostly it is. Okay, so assembly to machine is from 0 to many. Okay, so we talk about machine instruction set. Machine instructions like, are all these instructions are of the same length? How many cycles? We don't have the idea of how many cycles yet. How many cycles is determined by the organization and the logic level. Okay, here we just know add. We need to perform arithmetic add. Nothing else. Okay, are they of the same length? Are they of about the similar workloads? Do they go through about the same stages, same sequence of operations? Do they support complex operations like square root, division, or only primitive operations? Okay, the most complex being if, then, else, all packed in one instruction. Okay, so instruction set architecture determines how complex this can be, whether it's easy to pipeline or not. Okay, and if the VLSI implementation can be efficient or not. So last week I told you CISC, complex instruction set architecture, complex instruction set computer, CISC. The emergence of CISC is due to the incapability of the hardware. My hardware is so lean that I can do only very limited operation, so that the hardware has very limited capability, so that I need to have a micro program sitting in between my machine code and my hardware. And with this micro program, what else can I not do? Everything becomes possible because number of cycles is no more limited. Timing wasn't an issue at that time, wasn't a big issue at that time. So the instruction set becomes very, very complex. Many fabulous instructions, complex instructions, irregular instructions has been added in. Okay, and this instruction does not face the hardware directly. But in executing every of these instructions, even for the simplest add, you need to go through the microprogram, at least one cycle for micro instruction fetch, perhaps one more cycle for micro instruction decode, and then a few more cycles for source read, add, and result write back. So this add may take you 10 cycles, from 2, 3 to 10 cycles. So for CISC implementations, it's difficult to estimate the timing, the speed, plus it's very inefficient due to this indirection. Okay? People began to wonder, why not take this away and let my instruction set to interface with the hardware directly? If that's the case, then all my machine instructions will have to be simple, and they all better have some regularity among them. Okay, that's the basic concept of RISC. So we can save this overhead space-wise or timing-wise and make my hardware a lot faster. And if all these instructions are regular enough, then I can easily pipeline the execution of them. Pipelining saves a lot of, I said that wrong. Pipelining doesn't save hardware at all. It may even require more hardware, but it takes efficient use of all the hardware blocks, making the instruction throughput even higher. Okay, so now you understand what the instruction set is. And instruction set architecture means the features, all kinds of important features of this instruction set. And why do we talk about this? Because the instruction set architecture is a very important interface between software and hardware. What is this software? The software generated by the compiler, in other words, the machine code. We used to call it binary code, okay? Not assembly code, binary code. So the instruction set becomes a very important interface between the software and hardware, between compiler and OS, and even application. We call this software, and most software people don't have big problem understanding each other. And hardware people form another group. Usually hardware people have very limited or even no knowledge of software. So this is a big gap between two groups of researchers or designers. And we, computer architects, will have to understand both knowledge on both sides. We need to understand knowledge on both sides in order to make a good computer architect. Okay, so instruction set architecture, properties of good abstraction says, this doesn't have a lot to do with this. Any abstraction layer, like application programming layer, for any layer, a good abstraction of that layer should last through many generations. In other words, portability. For every 3 months, Intel will have a new version of the CPU. For every 3 to 4 years, Intel will have a completely different version of the next generation CPU. Okay, so from 1971 to today, after so many years, Intel is still using the x86 instruction architecture. So do you think x86 is a good instruction set architecture? We call it IA32 these days. Do you think it's good? The answer is it's lousy. It's only commercially good. It's only because the users are so widespread, making them stick to that instruction set architecture until today. A good instruction set can be used in many different ways. So we call it a general purpose. Okay, this is true for general purpose designs, but it may not be true for special purpose designs. So if I switch to another kind of processors, like graphic processing units, for graphic processing units, what do you mean by in many different ways? Does it mean graphics and video and security encryption? No, it doesn't mean that. It means within that scenario, graphics processing, you can do shading, transformation, lighting, Z-check, and color blending. Okay, you see? Only for graphics processing, there is still a lot of different uses in it. Okay? And provides convenient functionality to higher level. Do you understand compiler? Compiler is a piece of stupid software. It cannot be as smart as you are. So compilers will work very hard to first understand what the high-level program says. Scan, parse, lexical analyze, and then understand the semantics, knows what the application wants to do, then generate intermediate code, and then do the target machine binary code generation and do all kinds of optimizations. There are a limited number of registers it can use, how to allocate the registers, limited operations available, how to use those operations to implement higher level arithmetic operations like square root, like differential, integration. Okay? So all these are the tasks of a compiler. But since compiler is so dumb, it only uses the most simple binary instructions. For the complex instructions, compilers are not smart enough to fit them in the binary code efficiently. So eventually, compiler uses only the most primitive machine code. Try to imagine you are the compiler. What kind of instructions will you like the most? Simple ones, right? Easier to use. So how to provide convenient functionality to higher level? Make your instructions in the instruction set easily usable to the compiler, and permits an efficient implementation at lower levels. So for the lower levels, I just told you, all the instructions may be limited in functionality, may be designed so that they will go through the same instruction life cycle for easy pipelining. Example, the authors think that MIPS is a good example, a good instruction set example. Why is that? Because the two authors of this book are the inventors of the MIPS. MIPS is the nickname of a CPU. MIPS stands for what? Give me a guess. For RISC designs, the only genuine purpose of the RISC design is for pipelining. So in that whole book, we talk only about if I'm given only one word to describe the theme of computer organization course, the word I will use is pipelining. Okay, pipelining is so efficient so that we divide the life cycle of an instruction into several stages, like fetch, and then decode the instruction so that I know what to execute, and then sometimes you need to go to memory, and finally it writes the result back. So every instruction will be given these 5 stages. If you are an add, then I fetch you in, I decode and found out that you are an add, and then I do addition here. And since I don't need to use memory, I don't do anything here. And then write the result back into registers. Where do I read the source operands? Oh, while I'm decoding, I can read registers. Okay, even before I know what the instruction that is, I can start to read. Why is that? Oh, because my instructions are all of fixed length, say 32 bits. And my source 1 and source 2 fields are always fixed at here and here. Okay, so whatever I read from here, if you need them later, I got them. If you don't use them later, I simply discard them. Okay, so I'll never miss it. Okay, that's why I want the length of the instruction to be fixed. That's why I want the fields within the instruction to be fixed. Okay, even though this goal may not be achieved all the time, but that's my goal, trying to make everything as predictable as possible so that I need to have hardware within my CPU, maybe a fetcher hardware and whatever. And with all the hardwares available, my next instruction can begin execution right after, because here when I fetch and decode and execute in memory and write back, I'm using a different piece of hardware. My hardware will not conflict with yours. Later on, third instruction begins to execute. Fourth instruction begins to execute. Fifth instruction begins to execute. And when my pipeline is full, I found out that all my hardware will not conflict with each other. So all the hardwares are put in use. Very busy, very productive. One cycle per instruction will be completed. Okay, that's the so-called pipelining. Do you like that? The answer is you can't survive if you don't have that today. Everybody is doing at least pipelining. So with pipelining, we encounter some difficulties. Difficulty number one is when I do fetch, and if you're doing load store, then we will have memory conflict. Remember, von Neumann architecture says there's only one single memory. Both instructions and data are stored in that memory, right? So if you want to read the instruction and read or write data in the meantime, then your memory will be the critical, will be the conflicting resource. What do you do? What do you do? With two data buses? Okay, the memory is a very dense circuit with data bits packed in it. And there's only one rewrite port. If you want to increase the number of rewrite ports, say from 1 to 2, then you will need to have another set of rewrite buses, making the memory size almost doubled, which is very costly. Making such a dense circuit double-ported is very expensive, too expensive. You lose half of your capacity. So we have a smarter way, like what he says. Okay, so why not? In front of the memory, between the memory and the CPU, I give you two caches. One is called the instruction cache and one is called data cache. This is a fake dual memory design, but it works well. Okay, so I have two pieces of caches, making the CPU think, I do have two separate memory. One for data and one for instruction. Okay, very efficient. How big is this? This is only of the size of kilobyte. And this is of the size gigabytes or megabytes. So the size is 10 to the 6th order smaller. Okay, so this is the so-called pipelining, and you know more or less about the risk concept, risk philosophy. So far, any questions? ask questions. Maybe you don't have that background, but you need to build that background up. Otherwise, you're no more but a programmer.
So when you say risk is faster because it doesn't go through the microprogram.
Risk is faster because of several ways. Number one, there's no microprogramming overhead in between. Number two, even if the add instruction for RISC and for CISC take about the same amount of time, the RISC can pipeline. But the CISC is very difficult to pipeline. And in fact, if you want to pipeline it, maybe the length of each stage, pipe stage, is not balanced. And also you need to have a latch, a flip-flop, to record the intermediate result. So after pipelining, your life cycle will become even longer than in the CISC case. But it doesn't matter. Pipelining is always good.
So if somebody find that you need to add another instruction in a RISC architecture, does it mean you have to recircuit the whole CPU?
Maybe only the decoder, making the decoder be able to recognize the new instruction. But whatever instruction you want to add in, make sure it can fit in this culture. Okay? Don't make it look too weird so that everything will have to move around.
Because you have to fit it, is the instruction set naturally much simpler than the CISC instruction set?
If it's even simpler, then it's okay. When I say simple or complex, I mean if there are more or fewer stages required. Okay? So, in doing the pipelining, the first difficulty we need to encounter is insufficient hardware resources. Number two, if this one calculates a value which is to be used by this one, then the result will be available after the write back, right? Yet the result is required by this instruction at the end of the decode stage. So the result is not available until this point, but it is required here. So what happens? This result will have to travel back to the history, which is impossible. Okay, so that's the so-called dependency hazard. This instruction will need to be stalled, halted, until the result is available. We have very good schemes to solve this question, to solve this problem. Number three difficulty is if this is a branch instruction, and the branch is resolved at this point. So here, which instruction do you want to fetch? The subsequent one or the target one? You don't know yet. Even for this one, you don't know yet. So you may very likely fetch in the wrong instructions. Okay? And at this point, you begin to fetch the correct instruction if these two are wrong, and you will have to kill these two, wasting the previous effort. This is the third difficulty. So once resource conflicts may happen, data dependencies may delay your instruction execution, and branch may make your instruction streaming difficult. Okay, so we talk about only these three things in computer organization. And the main thing in that course is pipelining. Okay, so what is the name MIPS? MIPS stand for microprocessor without interlocked pipe stages. Now you see what makes a RISC microprocessor beautiful? Very smooth pipelining. Okay? So the name of this product line, microprocessor without interlocked pipe stages, says it all. It's not million instructions per second. We have a programmer storage within the microprocessor, okay, within the CPU. Like we have the registers, 32 registers. All these registers are general purpose, except for one. We always store 0 in R0. And if you want to write anything into R0, you cannot change this value. If you read from it, you always get the value 0. Why? Because the designer found it's convenient, it's useful to leave a register like that. And the rest are really general purpose. And then we have a program counter. The program counter is not a good name. A better name is instruction pointer. Intel uses the term instruction pointer. And the low and high register pair. These two registers are for multiplication. When you multiply 32-bit by 32-bit, then your result will be 64 bits long, which will be placed in the low-high. And then also we have 32-bit floating point registers not shown in this diagram. And the data types are all word type within the CPU. How do you define the word data type for a computer system? How long should a word be? How is word defined?
32 bits.
What?
32 bits.
Who said that? Never have a value for me. For definitions, maybe you shouldn't have values. Except for some terms may need to have values in it. Like define marriage, then one man, one woman. The values are very important. But the size of a computer word, the value is not important. And that's the most natural data type within CPU is to be defined the word. Okay? And for this microprocessor, the most natural size is whatever. I don't care. That is the word size. It happens to be 32. Arithmetic logical operations include these. Memory accesses include these instructions. And control include these instructions. And jump and link is the conventional call instruction. Call subroutine instruction, yes? Yes. Like an architect, when he draws the draft for a building, does it need to worry about sand, water, bricks, cement? Does it need to worry about those things? You may say no, but you may also say, oh yes, he needs to keep those things in mind. Okay? So here we only care about the instruction set. But there are a lot of related knowledge that we need to keep in mind, like compiler, like are we dealing with C language, or are we going to design a CPU for graphics? We need to keep all those in mind, okay? In this book, we deal with general purpose applications. All the instructions are 32 bits long, and they are aligned. They are aligned means the first address of the instruction is always something 00, and then 0, 1, 0, 1, 0, and 1, 1. Okay, all the instructions will have to be aligned in memory. Okay, so Mr. Amdahl, Blau, and Brooks said in 1964, the attributes of a computing system as seen by the programmer. This programmer may be the assembly programmer or machine code programmer. That is the conceptual structure and functional behavior as distinct from the organization of the data flows and controls, the logic design, and the physical implementation. So computer architects deal with the instruction set architecture only, and the instruction set architecture is only the conceptual structure and conceptual functional behavior of the CPU. And all the organization, data flow, and controls, and the bricks circuits are implied, only implied, but not explicit. Okay, it's just like how an architect drawing the draft for a new building. So, organization of programmable storage, how big is it? How can it be accessed, addressed? Data types and data structures, instruction formats, instruction set, modes of addressing and accessing data items and instructions, exceptional conditions. Think of the machine language that you're familiar with. Does your machine language specify how many bits addresses do you have? 32-bit address plus I/O device addresses? Yes, these are the so-called programmable storage organization. Okay, and data types and data structures. Can you access bits? Or must you access bytes, have words? Okay. An instruction format. When you use the instruction ADD, what do you need to put after that opcode? 2 operands, 3 operands, or no operand? Like for stack machine, you only say ADD. You cannot say anything else, because the machine will do pop, pop, add, and push. Nothing else for you to say. On the other hand, if you use addressable memory, then maybe you should say add source 1, source 2, destination. Okay? Anyone is missing, your code will not pass the decoder. We're talking about the machine code. And instruction set, what opcodes can I have? Mode of addressing. Addressing mode, do you understand that? Do you understand what addressing mode is? Some of you do. Give me some examples of addressing mode. You sitting in the back. Tell me, what kind of addressing modes do you know? What? You don't? Somebody want to try? Direct addressing. In other words, you specify the genuine full address of whatever you want to access in your instruction. What else? Indirect. Okay, you tell the instruction, go there and you'll get the real real address. Okay, go there and then you'll get the real address from there. What else? Immediate. If I want a value 4, then why not just put 4 in my instruction? Telling the CPU, that's the value I want to use. That's called immediate. You get the value right away. What else? Register. I say R1. Get my value from R1. That's the so-called register mode. Register indirect. Go to that register and you'll find the real address. Okay. PC relative. If a branch instruction says Minus 8, what does that mean? Oh, from the place where the where the current PC is pointing at, count back 8 instructions, and that instruction is the one I want to fetch. Okay, PC relative to the PC value. Okay, so there are many addressing modes, numbering up to 20, 30 possible addressing modes. Very good quiz question. Why do we need to have so many addressing modes? To give our students a drill? Just for fun? Flexibility only? Or we really need them? You want to speak up first? So you say that's for convenience? I doubt it for the time being. What's your opinion? It doesn't have to do with pipelining. Not yet. Pipelining has to do with the organization and logic design, particularly the organization. And addressing modes are also used for CISCs, those machines which are very difficult to pipeline. So it doesn't have a lot to do with pipelining. Okay, the answer is all the addressing modes are very useful. Sometimes you can't do without it. So you need to know when it is useful. For each and every of the addressing modes, you need to know when it is so useful that you will love it to death when you need it. Okay, like constant or immediate. If you don't have immediate, what do you need to do? You need to load that value into memory beforehand. And then when you need the value, you read it from memory. Remember, memory is very far away. Or if you need that value, but you don't have the immediate mode, then you need to hardwire that value in your CPU. Okay, so you see how important immediate is? PC relative. Without PC relative, your code is not relocatable. Do you know how you execute your code? You will tell the OS, hey OS, I want to execute my code. OS will say, okay, let me find you a space. Just like when you go to the restaurant and say, hey, I want to eat dinner. Then the waiter or waitress will lead you to a table. Do you know which table you will be seated before you go into the restaurant? You don't. Okay? So you will sit down at an arbitrary place. So when you want to branch to that instruction, do you know the address of that instruction? You never do. All you can say is it's 8 instructions above me. Remember? So without PC relative, you just can't do branching. Okay? So important that you cannot live without it. Okay, so you know addressing modes, and now you understand all are very critical. An exceptional condition. Some CPU says when there is an overflow, I'll signal the OS and ask the OS to handle this situation. Some CPU says if there's overflow, I'll signal but I'll continue. Some CPU design can say, I won't even signal it. It's all up to you. Okay? Or you can design instructions which will overlook the exception or handle the exception within the same instruction set. Some will overlook exception, some will handle exception. So, instruction set architecture versus computer architecture. Old definition of computer architecture is instruction set design. So now we know how important instruction set design is to a CPU design, or even to the efficiency of the whole computer system, because the CPU determines how information can be processed, excluding I/O time. Okay, but other aspects of computer design called implementation and insinuates implementation is uninteresting or less challenging. That was the old concept. Our view is, however, computer architecture is more than instruction set architecture design. Our computer architecture includes like memory system. Okay, memory sits right by the side of the CPU. CPU gets all the information from memory. So if the memory system is designed well, then the CPU can run a lot faster. That's why we talk about backup memory, main memory, and the cache memory. Okay. Architect's job, much more than instruction set design. Technical hurdles today, more challenging than those in instruction set design. Technical hurdles, technical barriers are things like, can I/O speed catch up? Can memory speed catch up? CPU speed somehow follows the Moore's law. Nowadays, we have over 5 gigahertz CPU clock speed. Why is that? That's due to pipelining. Okay, the semiconductor technology, this is a logic chip. Logic, by the term logic, I mean this maybe a CPU chip. It can do arithmetic, logical operations. And this is a memory chip. Both chips are manufactured from about the same semiconductor technology, so they have about the same transistor density, they have about the same die size. But however, the clock rate increase of these two types of chips, this is the logic chip, this is the memory chip. Long time back, the memory chip has higher clock rate. Here, this is the clock speed. Long time back, memory has higher clock rate because its structure is very regular. CPU has lower clock rate, but then CPU has a much higher clock rate increase than the memory. Do you know why? Because the whole memory chip should not be pipelined. Yet even we have the same chip size for the logic design, we can pipeline it so that the clock period deals with only local circuits. Okay, that's why we have a much higher clock rate increase for logic designs. Okay. So those so-called peripheries also matter. Since instruction set design not where action is, some conclude computer architecture using old definition is not where action is. But we disagree on conclusion. We think instruction set design is still important. Just we need to deal with more facets in the computer system design. Now, we do agree that ISA is not where the action is, but we do not agree that ISA is no more part of our computer architecture design, because we divide the whole chip into regions. So for every clock cycle, signal need to propagate through only a small region within the chip. Okay, like this is the fetcher When it's done, we can proceed to next clock cycle. But for the memory chip, these are the word lines, these are the address lines. We still need to propagate through the whole chip, from top to bottom, from left to right, okay? But we can localize these circuits. Yes, maybe you can, but then you need one cycle to determine which area I want to address, then next cycle to address into that area, then you need more cycles. Okay, it doesn't help. Nowadays, we also begin to pipeline the memory chip. How do we pipeline that? Row address decoding, column address decoding, and then word line charge discharge, and then output the result. We're beginning to pipeline the memory chip. So we do have some pipelined memory designs available nowadays. Okay, you can try that. Let your imagination fly. There's always room for advancement. Okay, so we care more about the complete system, not just the CPU, not just the memory, and not just one type of application. We need to know the whole spectrum of the applications, related applications, like what I said, triangular setup, coordination transformation, lighting, and then what else? Rendering, shading, okay, for the graphics. All the related phases of operation. So hardware matters, runtime system matters, compiler matters, everything else matters. And in networking, this is called the end-to-end argument. The last mile problem. Everything is important, especially when you reach at the last mile. And computer architecture is not just about transistors, individual instructions, or particular implementations. Computer architecture should make your computer architecture feasible for different kinds of technologies, TTL, PMOS, NMOS, CMOS, VLSI, until today, nanotechnology, and perhaps maybe tomorrow, photonic computing. Okay, a good computer architecture should last for long. For example, original RISC projects replaced complex instructions with a compiler plus simple instructions. Long time back, the compiler's task is easy because the CISC instructions do look somewhat like high-level language statements. So compilers can do easy translation, but the hardware is very inefficient. So nowadays, we think the hardware should bind directly to compiler. And we architect do the very important and critical interfacing between hardware and compiler. Then computer architecture is design and analysis. Architecture is an iterative process. Why do we say that? We need to search through the space of possible designs and at all levels of computer system. So beginning from somewhere, we want to have a system, an ideal system. Then this system will be divided into maybe software, hardware, and software includes operating system, compiler, and application, and hardware includes organizational techniques and the genuine circuit technology, like the semiconductor technology. We need to search through all the branches of this tree. And if you have a very creative idea, then you can move this wheel easily. If you have a bad idea, you will spend a lot of effort, but still maybe still not able to move this wheel. Okay, so this is a good idea. Easily improve your system's performance. Mediocre idea, the kind of ideas in between, and then bad ideas, maybe trying to improve the performance, but in vain. Next, how would you like this course? This is a course number at UC Berkeley. Okay, we can skip this page. This is the administrative thing. And typical class format. For 100 minutes, for the first 20 minutes, you can keep your attention. And then later, your attention curve goes down. And before I dismiss the class, your attention will come back again. So how do I keep your attention, level of attention high all the time? By making discussion with you, by giving you 1 minute break now and then. Okay, so raise any question you have. Tell me about any doubt you may have. Okay, I want you to understand. I don't care too much about the details, but I want you to understand. I will not come to class early to answer questions. I'll come to class on time, and I want you to raise questions in class. And I can stay late after the class. So Wednesday afternoon, usually I'll be in. So what about if I give you my office hours from 3:30 to 5:30 in the afternoon? Is that a good timing for you? Okay, so 3:30 to 5:30 will be my office hours. So quizzes. Would you like to have quizzes in the class? Yes or no? And if you fail this quiz, then you stay here overnight to study. Cannot go home. Okay, now let's see. Understanding the design techniques, machine structures, technology factors, evaluation methods that would determine the form of computers in 21st century. So, what is computer architecture? It has to do with applications, technology, programming languages, interface design, compilers, and we need to know a lot of history. Of course, we also need to understand operating systems. We need to know how to measure performance, evaluate the computer system, and also, most importantly, we need to explore parallelism. Did I tell you last week, how fast can light travel? You know how fast can light travel. But if I ask you, how far can light travel in 1 nanosecond? You see, all the circuits are operating at the gigahertz range. So for 1 gigahertz, the period is 1 nanosecond. So how far can light travel in 1 nanosecond?
0.3 centimeters.
How many centimeters? 0.3?
Oh, 0.3 meter.
Right. Light can travel that far in 1 nanosecond. And if you have a 10 gigahertz machine, light can travel that far, 3 centimeters, in 0.1 nanosecond. And in circuit, that range reduces to 1 centimeter. Okay? And your circuit, your die, is that big. Okay? So 5 gigahertz, 8 gigahertz may be the limit. The only thing left for us to do is to explore parallelism. Parallelism include place thousands of CPUs on one die. And then you should be able to use all these CPUs. And for your notebook, you'll have from 4 CPUs to 16 CPUs. Nowadays, 4 CPUs is the mainstream. So you should be able to write programs to fully use the 4 CPUs in your notebook. However, if you don't write any programs, then you're nothing but an ordinary user. So computer architecture is at a crossroad. Institutionalization and renaissance. Power, dependability, multi-CPUs versus one CPU performance. We cared about only one CPU performance, maybe in all your previous courses, but now you need to deal with many CPUs, so power becomes an issue. Dependability, communications, and parallelization of your application become issues. So here in this class, I like to mix my lecture with discussion. Any kind of related questions are welcome. And goal is to learn how to do good systems research. Don't make your vision too limited. Focusing on only a single point will never really solve the system problem. So you need to learn a lot from looking at good work in the past. At commit point, meaning the end of the semester, you may choose to pursue your own new idea instead. And these are some paper reading assignments, which is not for this course. It's up to you whether you want to read these papers or not. But anyway, as a graduate student, you're now a researcher. A graduate student is a researcher. A researcher should be interested in finding problems and solving problems autonomously. In other words, actively. You do that on your own. Don't let me force you to do research. Most information of importance to you will be in research papers, not in the textbook. In the textbook, all those are well-cooked materials. Everything is so fixed. Almost no new idea in the textbook. And ability to rapidly scan and understand research papers is key to your success. Okay? So English proficiency is important. Okay? I don't know why local students are so afraid of English, although they know it's so important. And by the way, do you understand my English? 10%? 20%? Or above a satisfactory level? Okay, that's good. So you will read a few papers in this course if you want. And papers will be scanned and on web page. No, I won't do that. You do that on your own since you are so internet addicted. You know how to do that. My daughter always tells her friends, my dad don't know how to use computer, which is true. I know how to design computer. It's just like that guy knows how to design a Ferrari, but doesn't drive well. Okay, so logic design maybe here, I don't know. But anyway, we build our knowledge up from here, some electronics, some circuit knowledge, and a lot of logic knowledge, and expertise in organizational knowledge, and then we're trying to become computer architects. And we need to know how the software will want us to be. We want the hardware system to be. So your graduate students coming from different fields or even different countries, you're with two varied background. In past, CS graduate students took written problem prelim exams on undergraduate material in hardware, software, and theory. So first 5 weeks, we'll review background. And prelims, we don't have it here. But prelims may be important for you to validate that you're ready for this course. It tells you if you're prepared for this course or not. And these course numbers are very confusing. Maybe I'll skip this part. COD means Computer Organization and Design. That's the computer organization textbook. We'll spend 2 lectures on review of pipelining and memory hierarchy, and in class quiz to be sure everyone is up to speed. So I have reviewed pipelining for you. We're not ready for the memory hierarchy review yet. So do you understand pipelining now? I don't care if I want to use more circuit because VLSI technology gives me all the circuit capacity I should need. The problem left is how well can you use these resources? Some people cannot. Some people knows how. Some people know how. And if for the hardware manufacturers, if they don't know how to use these resources smartly, then they begin to implement multi-cores, duplicate CPUs. But even if so, they still need to face the problem of how do I place the caches? How do I inter-network these CPUs together? They still need to deal with these problems, at least. Did we have a good review on pipelining? Any more questions on pipelining? So, short quiz. What are the 3 major difficulties in pipelining design? What?
Resource allocation.
Register allocation, wrong.
Resource allocation.
Resource allocation. There's a better, more formal name called structural problem. Okay. Number 2, dependency problem. Number 3, control problem, flow control problem, and control problem for short. And in the textbook, we call them structural hazard, dependency hazard, and control hazard. Hazard means there is danger. Hazard doesn't mean there is already a mistake. Hazard means you need to be careful. Okay, so you need to pick a project, and the instructor who made up this for you suggested a research platform which was built at UC Berkeley. I don't know. We don't have that platform here. So you can pick your own research topic, and if you have any doubt, talk to me. And I'll tell you if that's a good topic. I'll tell you what to do in that project. Okay. To help you learn. Yes?
By when is it a good time to decide? Because we're building our knowledge as we go.
If you want to get your grade at the end of this semester, then you may need to begin thinking in maybe a month and make decision at least in 2 months. Otherwise, your grade may be postponed. Okay, we're always pressed by time. I know this doesn't sound very reasonable because you haven't seen it all yet, but then you need to make decision. Okay, I know it's always the problem. But that's life. RAMP is the project name. So I'll skip all these. Every project as long as you can tell me the relationship with this course, with computer architecture, can be accepted, whatever, okay? But it depends on how well you relate it to computer architecture and how well you do in that project. You'll be assigned a proper score by me. Okay, so what computer architecture brings to the table? What issues it brings? Other fields often borrow ideas from architecture. And in designing anything, quantitative principle is important. Don't tell me how good it is. Just tell me how many customers will buy it and what profit you will get from each unit sold. That's the so-called quantitative principle, okay? I don't care how good you say it is. I just want to see it has a good sell and make good profit. So, in designing a system, we need to take advantage of parallelism and how many degrees of parallelism can I get? And we should use the principle of locality such that all the activities will happen locally to speed things up. And then focus on the common case because we always care about the majority more than the rarely happened cases. And then Amdahl's law tells us something when we get there. I'll tell you what Amdahl's law is. And finally, there is a processor performance equation. Whatever you say, there's a final ultimate equation to evaluate the performance of your design. That equation says, for a particular application, how much time you used on it. How much time can be divided into how many instructions you have executed and how many cycles on average an instruction would take and how long is a cycle. Okay, so that's the equation. I already gave you the equation. And whatever you have, another student will come up and say, hey, I have a better design. Then how do you know if yours is better or his is better? The answer is easy. Use quantitative comparison. Let them run and see which one runs faster or uses less power or whatever you care about. So we need to define, quantify, and summarize performance. If you have more than one system, then how do you relate their performance matrix? And then define and quantify cost. And if you have more than one system, do the same. And define and quantify dependability. You say, my system is very dependable. Then I will always reply with this. Give me a number so that I can measure it. Okay? So if you say, this guy is very dependable, what kind of number you think is proper? The number could be, he never tells the truth. Dependability is 0. Or 50% or 100%. Don't just tell me very. I don't catch your idea with the word very. Okay, I need a number. Okay? And define and quantify power. By the term power, do you care more about wattage or do you care about energy? They both are power. Do you know wattage? The energy burned within unit time. Do you know energy? From beginning to end, how many joules I used. So when I say power matters, do you know if I mean wattage or joule? Wattage, why?
Because different applications
Because it has to do with how hot this system will get. Because it has to do with whether I need to have a cooling fan, additional wattage, okay, noise, space. So anyone cares about how many joules? You do? Why?
You should care about that as well, because that has the cost.
Because it has to do with my electricity bill. Or it has to do with how long my cell-powered appliance can last. Okay, so do you care about wattage or joule or both? Depends. Okay, so now you understand power. Culture of anticipating and exploiting advances in technology. Being a computer architect, the architecture you design today may be used 2 years from today and may last for decades. So if you're going to design a computer architecture today, you should be able to foresee all the related technologies 2 decades from today, at least one, which is impossible in high-tech fields. Okay, you should be able to foresee technology changes and culture of well-defined interfaces that are carefully implemented and thoroughly checked. From application all the way to the job well done, there are levels of technologies, and every level of technology should have a very good interface between itself and the upper level, and also a very good interface between itself and the lower level, or even interface between itself and the several levels higher technologies. Okay, so well-defined interfacing is very important. How do we interface computer architecture to VLSI technology? Okay, so today when you want to design anything, you should know the chip circuit capacity could be 100 billion transistors, because it's 10 years from today. Okay, that gives you some kind of interfacing information. Okay, other than that, maybe 10 chips can be stacked together. Another kind of information which may be useful to you, and then maybe your PC board will remain the same size because of the physical limitation of light speed. Okay, and how much power? Due to environmental concerns, every PC board can burn only 1 watt of power. 1 watt only. Tell me, how much power will a most advanced CPU burn nowadays? Got any idea? Well over 100 for only one CPU. Okay, so we look at these topics one at a time, taking advantage of parallelism, increasing throughput of server computer via multiple processors or multiple disks. If you're running a server, then you have multiple different requests, queries from different users at the same time. So multiple processors will help. Multiple disks will help. And detailed hardware design, like carry-lookahead adders, uses parallelism to speed up computing sums from linear to logarithmic in number of bits per operand. So I can shorten my carry propagation chain. And multiple memory banks searched in parallel in set-associative caches. If you understand set-associative cache. And then pipelining, that's also a kind of parallelism. Overlap instruction execution to reduce the total time to complete an instruction sequence. So if you have a long instruction sequence, then the pipeline will speed the execution of this sequence up. However, for any single individual instruction, the execution times actually lengthened. Okay, so if you don't have sufficient number of instructions to be executed, the advantage of pipelining will not show. Not every instruction depends on immediate predecessor, the instruction right before it. So executing instructions completely or partially in parallel in a pipeline is very feasible. And then classic 5-stage pipelining includes instruction fetch, register read, execution. We do the instruction decoding also in this stage. Execution, data memory accesses. ALU and logical operations don't do memory accesses, right? So for those kind of instructions, the data memory access stage will be wasted. What do you think? What do you think? Some instructions or even many instructions don't use this stage. What do you want to do about it? Knock it out? Keep it in there? What do you say? Oh, quantitative approach. I want to know how many, what percentage of instructions we want to use this stage, right? So you do statistics and realize that loads and stores account for 40 or over 50% of the dynamic instructions. So is it worth to keep this stage in the pipeline? Maybe. Okay, as long as it's 20, 30%, maybe I want this stage. Okay. And then finally, if you get a result, then you want to do register write. Again, like for store instructions, I don't need this stage. For store instruction, I don't have register to write. For branch, I don't have register to write. So how many, what percentage of instructions will use this stage? Well over 70. Okay, all instructions need to be fetched, decoded, and executed. For loads and stores, what do? I calculate effective address here. Okay, pipeline the instruction execution. So instruction I, if this is the time axis, will be executed in these cycles, I plus 1, I plus 2, and I plus 3. And we notice something. Here we want to use memory. Here we also want to use memory. So we have two caches for instructions and data. And here we want to use register. Here we also want to use register. What do? Okay, we realize that register circuit is small. So if you want to write, the write would be completed in the middle of the way. It doesn't have to last for the whole cycle. And if we start our read here, although in the beginning the content is not what we really want, but after a while, if the content gets updated, we still have enough time to get the right result out. Okay? So we still use the whole cycle to write. Just the write will complete in the middle of the way. We still use the whole cycle to read. Just if the content changes, there's still enough time for us to get the right result out. If you have taken the computer organization course, in that course, your teacher told you something untrue. your teacher will say use the first half cycle to write and use the second half cycle to read, which is not true. Okay, the truth is that the write can still catch up to be read out. Okay? Got the idea?
We're not talking about the exact same register locations. We're just talking about registers on a whole and access to the register.
Right. And if it happens that the register you want to read is being written in the same cycle, that write can still catch up. If, however, it writes to different registers, then it doesn't matter at all. But we don't have any special circuit design to do half cycle write, half cycle read. No such a thing. What concept? Half cycle read and half cycle write? It comes naturally. I don't need any special implementation. So that's why we need to know something about the circuit. When the stored information changes, it still have sufficient amount of time to charge or discharge your bit line. Okay? So the timing still works. Limits to pipelining, we call them hazards. Hazards prevent next instruction from executing smoothly during its designated clock cycle. So we have structural hazard because two instructions attempt to use the same hardware simultaneously for two different purposes. If that happens, then we need to give it one more hardware. Data hazards, instruction depends on result of prior instructions still in the pipeline. So if you want to write here, but it intends to read the same register here, then this one will get the wrong result. But fortunately, the value is available here already. Okay, because after calculation, you have the right value. And this value, if to be used by this instruction, will really be needed at this time. You see? So forwarding may help. If I just run some wires directly from here to here with some gating, then I can determine whether I want the value read from the register, or if this register is being written by this instruction, then I run my information from this ALU directly to my ALU input in the next cycle. That's the so-called forwarding, very efficient and very cheap method. And control hazard, if I have a branch instruction, then how do I know if these two instructions are the right instructions that I want? So what we do is we can kill these two instructions if they're not the ones I want. Or we can predict whether this instruction will branch or not. How do you predict? Easy. I'll tell you how later. And how accurate is that? Do you know how accurate that is? 98% accurate. Is that high enough accuracy? That's why nowadays everybody uses branch prediction, almost no exception, because it's too easily predicted. Principle of locality. Even pipelining is a form of locality. It's a form of taking advantage of the locality. But when we talk about the locality, the most noticeable example is the memory system design. Okay, cache memory, virtual memory are the two most noticeable locality designs. So program accesses a relatively small portion of the address space at any instant of time. For locality, there are two different types. One type is called temporal locality, saying whatever you are using now, you may be using it very soon again. Okay, that's the so-called temporal locality. Like if you just caught John, maybe within a few days you'll call John again. Okay? And then spatial locality, which says whatever piece of information you use now, you may very likely use the nearby information very soon. Like if you caught student ID number 1, very likely you'll call number 2, number 3 again very soon. Okay? So temporal locality refers to the information itself. And spatial locality refers to the information nearby. Got the idea? Okay, very simple idea. And for the last 30 years, hardware relies on locality for memory performance. Cache memory was invented in 1968, more than 40 years ago. Okay, and virtual memory even earlier, yes.
For spatial locality, wouldn't that also mean that memory would have to be allocated close by as well?
When you say memory allocation, what do you mean? 2 different programs? Maybe not.
Not the same program, like it says addresses close by. I'm trying to see.
Right. So when you say memory should be located close by, do you mean like this is the program, then subsequent instructions should be placed next to each other in memory?
Yeah, exactly.
Yes, that gives us a very good spatial locality example.
But does that really happen?
It does. Whenever you execute this instruction, there's 80% of chance you will execute this instruction next. Why do I say 80% chance? Because out of every 5 instructions, there will be 1 branch. And for the branch, it's very likely to branch away. So that's why I say 80%. In fact, more than 80%. But less than 90%. So that's a very good locality, spatial locality. Okay, so for a memory system, if we take good use of the locality, then we can use a very small cache to capture the information which will be needed in near future next to the processor. Okay, this is a processor, this is a cache. How far away are they? They are virtually on the same chip, back to back. Okay, the bus distance could be called 0. And how far away is this memory? In addition to what I just told you, the clock rate is very low because it's not easily pipelined. It's almost impossible to be pipelined. In addition to that, this is usually in a different package if this is a DRAM. DRAM and the CPU uses different VLSI process technology. It's very difficult to mix these 2 designs on a single chip. Okay, although we now know how to do it. But it's expensive. Okay, so this is 100 cycles away. However, this is next to each other, 1 cycle away. So this is only like 1,000th of the capacity of this one. This one is big. Megabytes. This is only kilobytes. You want to make this bigger? Like 2 times bigger? Do you think that's advantageous? Do you want to make it bigger?
Make what bigger?
The cache. Make it twice the size. Then the miss rate will drop. Okay, for the circuit, I don't care. My VLSI has that capacity. If you don't use it up, it's your problem, not mine. And I'll sell you the chip still at the same price. Okay, so how to use it up depends on how smart you are. doesn't add any cost, additional cost to you. So that's not an issue. The real issue is if you want to make this cache any bigger than that, then maybe it cannot be accessed in one cycle. It may need that much time. And in fact, that's impossible. Maybe you need to increase the memory cycle to 2, making your pipeline deeper, worsening structural hazard, data hazard, and control hazard. We don't want the pipeline to be deeper. Okay? So that's why up to today, the first level cache is still only like 32 kilobytes. We rather add in another level of cache than enlarging this one. Okay? So the critical issue of level 1 cache design is speed, not miss rate. And the critical issue of the second level cache is now miss rate. Okay? Have you heard of that? The real design issue of a cache is speed, not miss rate. Have you heard of that? Maybe this is the first time. But very realistic, very important.
The second level is misread?
Miss rate.
Oh, misread.
Okay. Conventionally, whenever we talk about cache, we always care about miss rate and less miss penalty. But the truth is average access time. In a cache design, what you really need to care about is hit time plus hit rate times hit rate plus miss penalty times miss rate. This is what you really need to care about for a cache design, but the level 1 cache is very different. You care more about cycle time. Hit time, you care more about hit time. Okay. Because it needs to be fit in the pipeline. It should be balanced. It should be this first level cache cycle time is in play with all other stages. And all these are CPU components. The only exception is this. This is the level 1 cache. Okay, memory hierarchy. We have CPU up here. CPU gets information from registers, level 1 cache, level 2 cache, level 3 cache, level 4 cache, however many caches you have, and then main memory. Main memory nowadays remains only one layer, and then disk and then tape. And I told you how huge the capacity of a tape is compared with disk. Okay, but anyway, we call this secondary storage. Yet the program uses addresses of the disk, not the main memory. The program uses addresses from 0 to 4G for 32-bit addressing space, right? From 0 to 1111111, which translates to 4G. Yet we never have a memory so large yet. We used to have main memory of kilobytes only. Okay. How can things happen? Oh, we translate CPU address into main memory address. And we traditionally call that CPU address virtual address. And this main memory address, physical address. And in terms of the disk, How does the disk relate to virtual address? You tell me. How does disk relate to virtual address?
What do you mean by relate?
Okay.
It might store an indirect.
Is it in here?
Indirect addressing through memory.
I don't talk about this anymore. I talk about my program addressing space and the disk space. How do I relate this to this?
CPU takes care of that. Doesn't really matter.
Whatever takes care of that.
Operating system takes care of that.
Whatever takes care of that, I want to know the relationship first. The relationship is this virtual address from 0 to 11111 is only part in the disk. In this disk, I can have many independent virtual addresses, right? We can have many programs. By program, I mean OS is a program, compiler is a program, editor is a program. Everyone has from 0 to 4G space. All these are in here. So there are many complete virtual addresses in the disk. Got my idea? Right?
So the program keeps a reference of where its own virtual memory is, where its own memory is on the disk.
Program only cares about what address. It doesn't need to know where it is. Whether in disk or in main memory. It doesn't need to know. OS takes care of that. When I say OS, OS is huge. I should say Virtual Memory Manager takes care of that. Okay, back to this diagram. Time's almost up. So registers are used by whom? Cache is used by whom? Memory is used by whom? In other words, who can specify which register I want to use? Who can specify which register I want to use? Compiler or machine code writer, right? Okay, so it should be clear to you when I want to ask you the second question. Who determines how L1 cache should be used? So compiler says, oh, reserve this location for Mr. X. Reserve that location for Miss X. Can compiler say that? Never. So who uses cache? Never. Who uses cache? Never. Instruction doesn't even know if itself is in the cache or not. What are those things? Never heard of those. So who uses the cache? Nobody has the answer? Then the TA will give us the answer. Who uses the cache? TAs? Okay, hardware. Automatically. Whatever you want to use, I will make sure you have a location in the cache. If it's already in, that's fine. If not, then I'll find you a place. Okay? As time goes by, the information will be gathered in the cache, and then you will begin to have a steady hit rate, miss rate, whatever. Okay, so hardware determines how the cache should be used. Here and here and here. Long time back, we used to use software to use the cache, which is not very efficient. Remember, hardware is always faster. And any software should have hardware assist in order to run. Okay, so anything can be implemented in hardware directly, do that. Okay, so hardware determines how the cache should be used. Who determines how main memory should be used? Virtual Memory Manager. If there's a demanded page which is not in the main memory, OS determines where it should be placed. And OS knows whether another page will need to be swapped out. Okay, so OS determines how to use the main memory on a page basis. A page is usually several kilobytes large. And who determines how the disk is used? Who? Who? No, you. You determine to create a file. You determine that file should be deleted. OS cannot delete your file. Trust me. Okay? Okay, now you all know which one is used by what. And the size gets bigger. Per bit cost gets lower. And speed of access gets slower. Okay, that's for today. Any question before we dismiss the class?
Hardware dictates the L1 and L2, so how does that relate to locality?
Oh, hardware automatically captures that. Whatever is needed, I'll put it in here. And if it's full, still new information needs to come in, then the replacement policy matters. Whether I want to do least recent used, kick it out, or randomly kick one out, or whatever. So if the replacement policy is wrong, then the performance drops. You need to determine the replacement policy beforehand. And usually the hardware will give you a few to choose from. But still, once it starts to run, hardware does it. Yes? You say, what address is virtual? Virtual. No? This is virtual addressed, for sure. This one doesn't have so-called, this one doesn't have much addressing problem, okay, because they're all directly indexed. Okay, this one is okay, easy to deal with. Now, here and here and here, this is physical address for sure. This is physical, this is virtual. So when will virtual address be translated into physical? Could be here, here, or here. Doesn't matter. So caches can be virtual addressed, can be physically addressed. Either way, it has its advantages or disadvantages. So it depends on your need. Okay? And this is physical, and this is virtual again, plus file ID. Your program is nothing but a file. Okay?
Those virtual addresses are maintained on the CPU itself, right?
CPUs are given those addresses. CPU doesn't know what kind of address that is. But we, as the God, we know that's so-called virtual. We call that virtual. CPUs are given those addresses. It doesn't know what those mean, and it doesn't do anything to change that.
So a CPU is given an address, and it translates into a physical address at level 1, level 2, and memory, and see which level does it hit.
Right, somewhere in here.
After it hits, the search to the next.
It's up to you. Whatever address you want your cache to use is fine. Okay, but each one has different problems. Okay, CPU is only given the address from 0 to 11111. And it doesn't do any changes to it.